Howdy, y'all. So I just wanted to go over naming ionic compounds a little bit again because I did it real quick in class. Feel free to come to office hours or email me if you have any questions about the stuff that is homework on Thursday that I went through really fast on Monday. I will be happy to answer those, especially lattice energy. Lattice energy is kind of hard to wrap your head around, but it's just using Coulomb's law like we did before. So you should be a expert at Coulomb's law by now. So you'll just want to keep that in the back of your head when you're doing lattice energy. Anywho, I'm going to start with naming ionic compounds. So the naming of ions and compounds is called nomenclature. So this is something that chemists are very particular about, is the nomenclature. So especially if you go on to organic chemistry, there's a whole naming system. It's called the IUPAC naming system. I don't remember what that stands for off the top of my head, but it's a very particular way of naming molecules and compounds that is used throughout the world. So just like our just like our scientific um, units, just like our SI units that are used by everyone throughout the world, the nomenclature for naming ions, compounds, organic compounds, etc. Those are common throughout the world so that everybody knows what everybody else is talking about. It's very important for sharing science, which is one of the steps of the scientific method that we learned way back. Anywho, main group cations, when we're naming these, the main group cations keep the name of their element, and then we tag ion on the end. So potassium, so K plus is the potassium ion, calcium 2 plus is the calcium ion, aluminum 3 plus is the aluminum ion. They have the same charge all the time. The group 1, group 2, and group 3, well, group 1, group 2, and group 13 ions always have, well, that's not true, but group 1, group 2, and aluminum always have the same charge, so we don't need to specify the charge anywhere in the name of the ion. Transition metal cations, on the other hand, which we talked about a little bit last time, these transition metal cations, they can come in different charges because of their unique electron configurations. So we have to specify the charge of the ion using Roman numerals, and we keep the element name and add ion on the end. So iron, so Fe2 plus is the iron 2 ion, Fe3 plus is the iron 3 ion. They used to be called the ferrous ion and the ferric ion, but we don't use that terminology anymore because it's definitely more well-known, more commonplace. Everybody knows what you're talking about when you say iron 2 or iron 3. Ferrous and ferric can get confusing because, little known fact, there's also an iron 1 plus ion that is possible. And what do we call that? Don't know. So that's why we use the Roman numerals instead of the Greek endings. All right, and then anions. Non-metal anions, we change the element ending to "ide" and we add ion on the end. Again, we always add ion on the end. So the chlorine minus, that's called the chloride ion. O2 minus is the oxide ion. So those are the endings. We change chlorine to chloride. We change oxygen to oxide. We just change the ending and add ion on the end. Very simple. And we have a nice list of all of the different common cations and anions. You don't need to memorize most of these. So aluminum is one that's always the same. Barium is based on its group 2 placement, so it's always 2 plus. So you should be able to either memorize these or identify them based on the place on the periodic table, but you don't need to memorize things like chromium 3 plus. You just need to know that if you see chromium with the 3 in Roman numerals, that's the chromium 3 plus ion. If you see copper with 2 Roman numerals in the parentheses, that's copper 2 plus ion. So you don't need to memorize these per se, but you just need to know how to read the naming of these ions. You don't need to memorize that silver is a 1+ cation. That one's a little unique, not one that you need to memorize per se, but it's always the case that it is silver plus. And then all of our anions, their charges come from where they are on the periodic table as well. Our halogens are all 1- anions. Nitride is a 3- because it's in group 15. So 15 minus 18 gives you -3 for the charge. Oxide is 16 minus 18 gives you -2 for the charge. Same with sulfide, 16 minus 18. So this is just some common cations and anions for you to recognize. All right, and then we talked a little bit about this in class on Monday. So I was saying that potassium bromide is how we would name the KBr. So the formula is KBr. There's one potassium ion, one bromide ion, and when we combine them, we call them potassium bromide. And that's based on the charges. A +1 and a -1 gives us a neutral charge of 0 on our compound. Zinc iodide. We've got the zinc 2+ ion and the iodide 1- ion. They combined form zinc iodide. Zinc has a 2+ charge and iodine has a 1- charge. So we need 2 iodide ions to balance out the +2 on zinc. So we multiply it by 2, and that's where we get our little subscript in the formula. So the formula is zinc iodide with a little 2 subscript, and that takes care of our charge. So the charges add up to 0. And then aluminum oxide is a little more complicated because we have a +3 charge and a -2. So now we have to find the common denominator or the common multiplier, I would say. But the easy way to do it is to just move the charge on the cation to the subscript of the anion. So +3 of the charge on aluminum goes to a 3 in the subscript for oxygen. O2 minus, the 2 minus, ends up as A2 in the subscript for aluminum. So we have 2 + 3 aluminum ions in our formula, and that gives us +6. We have 3 - 2 oxygen ions in our formula. That gives us -6. So together we get a neutral charge of 0 on our compound. And our formula is Al2O3 for aluminum oxide. So we could write some formulas for these ionic compounds. You can pause here and write these formulas. So these are all going to be based on the ions. So aluminum ion is our Al3+. Fluoride ion is a halogen, so it's an F-. So I'll write these out for you. Copper with the 2 in the Roman numerals is copper 2+. And the chloride ion, chloride is again a halogen, so it's a 1-. Iron is the Fe, and it's got a 3 here, so that makes it a 3+ ion. And oxygen is a 2-. It's in group 16. Okay, sodium, we've got, sodium is a group 1, what's the word, main group metal ion, so it gets a +1 charge. And phosphide is in group 15, so the common way of finding the charge is 15 minus 18, so we got a -3 charge on phosphide. And then calcium's group 2, so we get a 2+ charge. And sulfur or sulfide ion is right below oxygen, so we end up with a 2-. So when we combine these, we have +3, so we need 3 of these to balance it out. So +3 plus 3 times -1 gives us a neutral compound, so that's AlF3. Copper has a 2+, so we need 2 chlorides to balance it out. So +2 plus 1 times 2 times -1 gives us a 0. So we write that one as CuCl2. And all right, so iron 3 plus and oxygen 2 minus. This one's going to be like our aluminum oxide on the previous slide. So this one's going to be Fe2O3. So that the 3 ends up as a subscript for oxygen, the 2 ends up as a subscript for iron. Okay, sodium. So now we have the opposite problem. We have a small positive charge and a big negative charge. So we need to do the same thing. Now we need 3 positive sodium ions to balance out the -3 charge on phosphide. So we'd write this one as Na3P. We have 3 sodium ions and 1 phosphide ion. And then calcium and sulfide. Oh, we got a +2 and a -2. So that one is actually going to be CaS. And we don't need any subscripts on that one because +2 minus, or +2 plus -2 equals 0. So we don't need to change anything there. It's a 1-to-1 ratio, our formula. All right, and then naming these compounds is pretty easy. So sodium plus the bromide ion gives you sodium bromide. Calcium plus the fluoride ion gives you calcium fluoride. Lithium plus the nitride ion gives you lithium nitride. And sodium plus the sulfide ion gives you sodium sulfide. The compounds, so when you have our transition metals, we just keep that Roman numeral again. So now we got iron 2 chloride, iron 2 chloride or iron 3 chloride respectively. And all of that is summed up in this flow chart over here. Okay, awesome. Let's keep going. Oh, so now we can name the ionic compounds that we just made before. So we've got aluminum and fluoride. So that's going to be called aluminum fluoride. We've got copper 2 and chloride. That's going to be called copper 2 chloride. We've got iron 3 and oxide. So that's going to be iron 3 oxide. You see where I'm going with this? Naming naming ionic compounds is super easy once you know the names of the ions themselves, okay? Finding the formula is a little harder, but you just have to remember what the charges are based on the group of the metal cation or the group of the non-metal anion to remember what the charges are. Then you just gotta make them cancel out, gotta make them add up to 0. Okay, awesome. Let's learn about something new. Oops, sorry, had that one in there twice for some reason. All right, so now we're going to talk about covalent compounds. Covalent bonding comes from when we have 2 nonmetals bonding with each other. So this is kind of a graph that explains how covalent bonding works. So if you remember Coulomb's law, we have positive charges and negative charges is favorable, whereas negative is unfavorable, or positive is unfavorable. So that comes from this area right here. So when we're making the H2 molecule, so hydrogen and hydrogen combined to make a molecule, we need the atoms at just the right distance for a stable bond. So when they're at just the right distance, the positive charge on the nucleus and the negative charge on the electron of the other hydrogen atom have a really good interaction and we form a bond. When they're too far apart, the attractive force isn't strong enough, so we don't form a bond. When they're too close together, the repulsive forces dominate. So the electrons in the 2 hydrogen atoms repel each other, and the positively charged nuclei of the 2 hydrogen atoms repel each other. So when they're too close, we have repulsive forces. When they're too far away, we have basically no forces. And at just the right distance, for hydrogen, it happens to be 74 picometers, we have a bond form. So they're just the right distance, and we have positive charge in the nuclei interacting with the negative charge on the opposite atom's electron. Cool. All right, so this is just summing that up. When the attraction between the nucleus of one atom and the electrons of the other atom is greater than the nuclei-nuclei repulsion and the electron-electron repulsion, we get a bond forming. So the attraction has to outweigh the repulsion between the two atoms. When that happens, we form a bond. And what does a bond mean? So in terms of covalent compounds, a bond is the sharing of the valence electrons. So the electrons are shared between the two atoms. The valence electrons pair up to fill the 1s orbital for hydrogen. So we end up having so each hydrogen atom has one 1s electron. But when they are combined, when a bond forms, both of those hydrogen atoms simulate having a noble gas configuration. They simulate having the electron configuration of helium if both of them are sharing both electrons. So both hydrogen atoms are sharing the two electrons, so they both have a shared noble gas configuration of helium. Cool, right? So that's what it means to form a covalent bond, sharing of electrons to fill orbitals and to achieve noble gas configuration. And a molecule, that's the definition of a molecule, is the combination of two or more atoms held together by chemical bonds, covalent bonds. And this is just showing the attraction, like this. So the H is representing the nucleus of our two atoms, and the little circle is representing our electron. So the attraction of the electron to the nucleus of the opposite atom is greater than the repulsion between the two electrons or between the two nuclei. We end up with a bond. So we have our Lewis symbol, our Lewis dot symbol for hydrogen is just hydrogen with one little valence electron. And when we put them together, those two little valence electrons pair up, and we draw that bond that forms as a dashed line between the two hydrogen atoms. All right, so do you guys remember back to when we first learned about Dalton? Dalton, he had this atomic theory, and the first part we learned back in chapter 2 was that elements or matter is made up of atoms or molecules of the same atoms. So elements like hydrogen, helium, whatever, they're made up of atoms of hydrogen, helium, whatever. So those, all matter is made up of atoms. That was the first part. And the other part of that was also that atoms of one element are different from atoms of another element. So each element has unique atoms. The atoms are and the atoms of a single element are identical. So they're distinct from each other, they're distinct from other elements, but they're all the same when they're formed of the same element. All right, so now moving on, Dalton's atomic theory also talks about compounds. So compounds are formed when atoms of two or more elements are combined, aka they react. And this definition of a compound, the formation of two or more different elements, is not just a random combination. The compounds also, they always have a fixed whole number ratio of one element to another. And that comes from an even older law before Dalton, by this guy named Joseph Proust, the law of definite proportions. Every compound has a fixed whole number ratio of one element to another. So if you take carbon dioxide, for example, like your book does, no matter where that carbon dioxide is found, if it is carbon dioxide, if it's pure carbon dioxide, the ratio of oxygen to carbon is going to be the same. No matter where you find the carbon dioxide, if it is carbon dioxide, that ratio is fixed for that compound. It's always going to be the same for any molecules of carbon dioxide. And they analyzed that with some different samples. I think they said they were from Mexico. In your textbook, you can take a look at that. But the main point is this ratio over here, always the same. There's always 2.66 grams of oxygen for every 1 gram of carbon in carbon dioxide. So that ratio is always the same. And that's looking at masses, that's not looking at moles. So we'll talk about that a little bit later. So Dalton was like, okay, cool. So what else can we do with this law of definite proportions? What else can we do with these ratios that make up different compounds? So he came up with the law of multiple proportions, which is very similar. The two elements are forming a compound, and that compound has a fixed ratio of the two elements to each other. But he also took into consideration that two elements can form more than one type of compound. For example, we've got carbon dioxide and carbon monoxide. They're both made up of only carbon and oxygen, but they're two different compounds. They've got different molecular formulas, and they've got different ratios of oxygen to carbon. But the funny thing is that the mass ratio of the elements between the two compounds is always a ratio of small whole numbers. So what does that mean? So on the previous slide, we had carbon dioxide. The ratio of the mass of oxygen to the mass of carbon was 2.66 to 1 for carbon dioxide. For carbon monoxide, it's 1.33 to 1. So it's different, but look at those two numbers and how they compare. Those two numbers are a whole number, or a ratio of small whole numbers, 2 to 1. And if we look at it in terms of the atoms, or the moles of atoms, we've got 2 oxygen atoms for every 1 carbon atom in carbon dioxide. We've got 1 oxygen atom for every 1 carbon atom in carbon monoxide. So if we divide those ratios, so the oxygen to carbon ratio in carbon dioxide, we divide that by the oxygen to carbon ratio in carbon monoxide, and we get a ratio of small whole numbers, 2 to 1. So it works out with the mass, and it works out with the number of atoms. So that's pretty cool. So that is explaining how compounds work. They are always made of the same things. So carbon dioxide is always made up of carbon and oxygen in that ratio. It's always carbon with 2 oxygen atoms. And every other carbon oxygen compound is related to carbon dioxide in a way based on its mass and number of atoms. All right, cool. So you might do something with that in your homework, but that's going to be it for Dalton's atomic theory. I'm going to pause here and start another video.